This video will demonstrate how to use the PID controller that is built into our Commander Series VFDs. The topics I will cover are PID control basics, drive commissioning for use with the PID controller, PID controller settings, PID controller testing and tuning. Be sure to see the comments in the video description for links to both global and US technical support, should you require technical assistance. So if you're ready, let's get started. A PID controller is used to regulate a process variable, such as liquid or airflow. P, I, and D stand for proportional, integral, and derivative. These are gain terms that the PID controller will use to reduce errors in the process variable. A PID controller is a closed-loop system. That means that the controller will automatically adjust its output to compensate for any process error that is measured using a process sensor, such as a flow meter with an analog or current output signal. Our Commander Series drives, as well as our Unidrive drive family and our micro drive, the Commander S100, all provide a PID controller as a standard feature. Let's take a closer look at the PID diagram and start to fill in some of the pieces we'll need for this application. First, the set point for the controller, which represents the desired flow rate, will be entered using the keypad on the Commander drive. Of course, it could come from an HMI or a PLC too. Next, the feedback, which represents the actual flow rate, will come from a digital flow meter. The flow meter's output will be wired into an analog input on the Commander drive. You need to know what type of output signal the meter will provide, as that will determine which of the two analog inputs on the Commander drive to use. If the meter provides a 0 to 10 volt DC output, you can use either of the analog inputs. However, if it provides a 4 to 20 milliamp signal, it must be wired into analog input 1. Finally, the output of the PID controller is going to be used to adjust the speed of the motor which is controlling the pump. The PID error signal may be positive or negative. If the error is positive, indicating too much flow, the motor will slow down. If the error is negative, indicating reduced flow, the motor will speed up in an effort to maintain the user's desired set point. Now, let's see how to configure the drive parameters for this application. Before configuring the PID controller itself, it is important to do some basic drive commissioning first. Specifically, enter your motor nameplate data, perform a stationary auto-tune, select the drive configuration, or where the speed reference will come from, and then finally, adjusting the switching frequency. In the video that follows, I'll show you how I've got my Commander drive configured to this point. Let's have a look at the basic commissioning parameters that we're going to need for our PID controller. As you can see, I have Connect software open and I have begun a new project for my Commander C200. And I am currently online with the drive using our SI Ethernet module that I've installed into the expansion slot on my Commander C200. If you don't have an SI Ethernet module, you may also use Connect software by using our model number AI-485-adapter, serial communication adapter, and our CT-USB-cable, serial cable. So let's get started with the commissioning. This drive is in out-of-box condition, so I'm going to begin by expanding the parameters folder, and I'm going to try to work mostly in menu 0, which is called the Quick Setup menu. So I'll double-click that, and here are the contents of the Quick Setup menu. Now, as you can see, all of the parameters are at their default values because anything that I change will be highlighted in light blue. So as with any new application, I always begin by entering my motor nameplate data. So that's here at parameter 6. So my motor rated current is 0.6 amps. The motor rated speed is 1710 RPM. It is a 230 volt motor, and the power factor is 0.6. Now that I've entered my motor nameplate data, the next thing I'm going to do is to perform a stationary auto tune. This isn't entirely necessary when the drive is being operated in open loop mode, but it is beneficial. So back on the dashboard, I'm going to come to the setup and then auto tune. This is the auto tune wizard. And I am going to do a stationary auto tune, so that's checked by default. I'll click Next. There's nothing preventing me from performing the auto tune, so I'll click Next. And now I'll begin the auto tune by closing the drive enable or the safe torque off input. And the auto tune has begun. You can tell that because it says in progress and the elapsed time is incrementing. It's now finished. It was successful. There were no trips. So before I can move along, I'm going to need to remove the drive enable. And now my next button is active. And here are the things that were measured during that test. And here were the parameters that were updated as a result. So I'll save those parameters in the drive. There. Now let's go back to menu 0 and I'll look at a few of these other parameters. I'm going to start with parameter 5, which is drive configuration. By default, it is in AV mode. And if you were to look at the help, that says that the speed reference is going to come from analog input 1 or analog input 2. What I like to do when I do new applications like this one is I'll always begin by changing this to keypad mode. Now the reason I do that is because I want to make sure that I have full control of the motor and that the motor is rotating the correct direction. We don't want the pump to run backwards. Now, after I've finished my initial testing, we're going to come back here and I'll demonstrate this. We're going to put the drive in PID control mode. But for now, we're just going to leave it in keypad. Now, some of the other parameters that are going to be important, the PID controller settings are in menu 14. And by default, parameter 10, which is the security status, is at level 1, which will prevent access to menu 14. So I'm going to change this to all menus. And the other reason I do that is because we're going to be using the keypad to enter the set point for our flow. So I'll need to change that to all menus so that the operator can get at that parameter. Now, as I move down, some of the other things in here, this is important. My flow meter outputs a 0 to 10 volt DC signal, so I'm using analog input 1. And by default, the analog input 1 mode is voltage, so I do not need to change anything there. I'm going to move down. The next thing I want to change is the switching frequency, which is parameter 37. This is important if you are operating in an environment where acoustic noise from the switch frequency in the drive is important or would cause interference, like an HVAC application, for example. So what I'm going to do is I'm going to change this. Now there is a trade-off here. The higher the switch frequency, the quieter the operation will be, but it will also cause the drive to work harder, and you may end up with heating issues. So rather than jump all the way to 16 kilohertz, I'm going to choose a more conservative 8 kilohertz. That will quiet it down and improve our performance. For now, these are the only things that I am going to require. So before getting out of the software, I'm going to save the parameters in the drive, and then I'm going to finish by uploading from the drive. Now we're ready to begin looking at menu 14, the user PID controller. The PID controller settings are found in menu 14. What you're looking at is the block diagram representation of menu 14 that is taken from the block diagrams view in Connect software. The rectangular boxes in this diagram represent submenus, and I can click on them to open those menus. I can also edit parameters directly by double-clicking on them. In the video that follows, I'm going to demonstrate how to configure the PID controller using this block diagram. Okay, let's set up the PID controller. As I mentioned, the first thing I'm going to do, now that I have tested my motor using keypad mode, the pump does run the correct direction. The first thing I'm going to do is change parameter 5 in menu 0 from keypad to PID control. Now, having made that change, it's also important that you reset the drive so that the control terminal configurations, which do get changed as part of this macro, are updated correctly. So I'm going to come up to the control ribbon and click Reset now. All right. Now what I'd like to show you is I'm going to open the help a little further. And specifically, I want to show you what happens when you change parameter 5 to PID control. So if I scroll down the list, I see here PID control. Puts the drive in PID mode, and analog input 1 is a current feedback source. Analog input 2 is a voltage reference source. Well, for my application, that's not going to work because my flow meter is wired into analog input 1, and as I mentioned, it produces 0 to 10 volts DC. So I'm going to need to go into menu 7, which is here, and change analog input 1 from current to voltage. The other thing you can look at to see what else happened is if I scroll down a bit, you see this chart. If I look at the PID column, it also changed menu 1 parameter 14 to a 1. Analog input mode, this is the parameter I'm going to need to change back. Menu 7, parameter 7. So you scroll down this column, you can see the other things that were changed when I put the drive in PID control. So now let's go look at menu 14, the PID controller. I'm going to expand the block diagram folder, and I'm going to double click here. This is the diagram I showed you earlier. And again, the parameters that you see with question marks that are in a graphic that looks like this, or in a rectangle that looks like that, I can double click here and edit those parameters directly if I would like to, and I'm going to do that as we move along. But what I want to point out first is there are two submenus here, as indicated by the box that you see: PID control and PID1 source. I'm going to begin by opening the PID1 control. And menu 14 parameter 8 is PID1 enable. Now you probably didn't catch it, I didn't point it out, but when I put the drive in PID control, one of the other things that it did was it changed the function, the control function for digital input 5, and Now, digital input 5 on the control terminal is going to be used to enable and disable the PID controller. And I'll demonstrate that for you by turning this input on and off. There it is. Now it's off. So we have the ability to enable and disable the PID controller using the control terminal number 5. Now I'm going to use the back button to go back to my diagram. And let's next look at PID1 source here. So this section up here, that's the source. Down here is the feedback. So what I'm going to do is I am going to let the user enter the set point by changing menu 14 parameter 25. I'm going to disable analog input 2 as the source by setting that to 0 and clicking OK. And you'll see it changes to question marks. And once again, anytime I change something in menu 6, 7, or 8, it requires a reset to take effect. So before I forget, I will do that. There we go. So my set point is going to come from menu 14 parameter 25. I'm also able to scale my reference using this parameter 1423 as a multiplier. I don't have a need to do that right now, so I'm going to leave that at its default value of 1. And while we're speaking of the reference, the units for the set point are in terms of percentage with a range of 0 to 100%. The Commander C200 does not provide a mechanism for creating custom user units, whatever you have, liters per second, things like that, flow units. The units will always be in terms of percent. One of the things that I do while the drive is in keypad as well, while I'm testing the motor, is I run the pump up to 60 hertz while looking at my flow meter, and that will give me an idea of what the capacity of this drive and motor is for creating flow. So I have an idea of what 100% relates to in terms of the flow on my flow meter, but in terms of the units here on the drive itself, it's always going to be in percent. So as we flow through, anything that's in a diamond like this, that is read-only. So you'll see once we get started that there'll be a value there that'll represent our set point that we entered here. I can also invert the reference if I would like to. I'm not going to do that at this point. The slew rate now, we might come back and adjust this. This has to do with the rate at which the PID error, which will be shown here, is reduced. So if I were to put a value of 1 there, that means that whatever error would be shown here will be corrected within 1 second. So this has an effect of sort of detuning the process loop to make it more or less responsive to the error. So let's stop right here. That's the set point. Down here is where the flow meter comes in. And right now, the PID feedback source is analog input 1, but the mode is in current. Now I know that my flow meter is wired correctly, but it's not showing anything here. And that's because, as I mentioned, I need to change analog input 1 from its current setting of 4 to 20 back to voltage. So I'm going to change the mode up here in the parameters, menu 7, analog input 1 mode, see? 4 to 20. I'm going to change that to voltage. And once again, I've made a change to menu 7, so I'm going to need to reset the drive before that takes effect. Now let's go back and see what it looks like here. Okay, 701 is now analog input 1. I'm not going to be using the digital feedback. I'm using the actual feedback from the flow meter. I could scale the feedback if I would like. And the value for the flow meter would be shown here. Notice the units are in percent, as I mentioned. I could invert the feedback if I would like, but I'm not going to. So that's the foundation of the PID controller. We have a set point, which is going to come from menu 14, parameter 25. And then we have feedback, which is going to come from analog input 1, which is now in voltage mode, so it will accommodate my flow meter. The difference between the set point and the feedback is error, and that's shown in menu 14, parameter 22. So now let's go back and look at the PID controller itself. So we have the source configured and the control configured. There's the error, which is the output from here. The error is then processed through the gain terms, proportional, integral, and differential. In the next video, where I'm tuning and testing, I'm going to be changing these to show you what effect they have. One thing I will say right off the bat is integrator hold enable is probably going to need to be turned on. I'm leaving it off for now, but the integral term in the PID controller is additive, which means that the gain value to correct for error is added over each successive scan. And what that ends up with, if I don't turn this on, is I'll get what's called integral windup, where the value will just keep increasing and increasing and increasing. Not this value, but the output value of that gain term will keep increasing, and it will get to a very large value and could cause instability. So I will probably turn that on when we get to testing time. Now here is the output upper and lower limit of the PID gain structure. And by default, it's 100 plus 100 minus 100. Symmetrical limit enable is off. So what I could do is I could make this minus 40, for example. Instead of plus and minus 100, that can be plus 30, that can be minus 60, only when that's off. I'm going to turn that on because I don't need to do that. The PID output will be shown there, and once again, it's in terms of units. I could scale the output by using this multiplier if I would like. And then finally, the PID controller output is going to be menu 1 parameter 36, which is analog speed reference 1. That's what I'm going to be using to control the speed of my motor. The other thing that you can do, and I'll show you this in the next video, is you can include what's called a feed-forward reference. And what this is, if you literally follow the schematic, is this is a term in percent again that I can use to sort of kickstart the PID controller. Instead of waiting for error to develop here and then come up here, if I were to add a small value here, I could start the process a little faster. I don't know that that will be noticeable, but I'll turn that on when we get to the demonstration portion. So for now, that's all I need to do to configure the PID controller. So as before, I'm going to save parameters in my drive and then upload. Next, we're going to look at testing and tuning. One of the more popular methods of controlling the commander drive when using the PID controller is to incorporate a hand-off auto 3-position selector switch. The wiring diagram shown here represents how I've configured the digital control terminals in Menu 8 for this example. I used logic function 1, which is located in Menu 9, to logically AND the state of the run forward sequencer function with the state of digital input 2, that is the drive enable terminal on the commander drive. When the selector switch is in the hand position, it puts the drive into keypad mode, and the operator can run the pump using the buttons on the drive's keypad. In the off position, the drive will idle. In the auto position, the PID controller is enabled and the pump will be under PID control. Use this diagram as an example. As always, you must adhere to all local, state, and federal safety regulations when operating machinery. I'm going to demonstrate how the PID controller operates now, and I'm starting by showing you that I have all of the gain terms for the PID controller set at their defaults. Basically, everything here is all at the default setting, which is a good place to start. If you were to look at the help, which I've shown here for Menu 14 Parameter 1, it goes through and discusses how the PID controller output is calculated. And it comes down to the formula that you see right here, which basically states that the output is a result of the error multiplied by your gain terms that you have here. There have been a lot of articles written about how to tune PID loops. In the end, I think my best advice is that it's going to be a trial and error, particularly as the controllers or as the applications from system to system vary. So I'm just going to be showing you what happens if I were to make some changes and how it results or how it affects the output. So the software that I'm going to use to demonstrate this is our software oscilloscope program, and that's called CT Scope. This software is available for download from our website, and once it's installed, you'll see the icon for it here in the dashboard be active. So I'm going to launch that software now, and this is what it looks like. And I'm going to create a new multi-channel scope right there. So I'll click OK. The first thing I'll do is choose the correct drive. So I'm working with a Commander C200, so let me move down. There it is. And I am in open loop mode. So the window of the virtual oscilloscope here is divided into two panes. The top pane up here will show any digital channels that I have mapped. And you can see down here, analog, digital. And then the bottom will be any analog channels that I have mapped. So I'm going to begin by mapping a digital channel. And specifically what I'm going to look at is Menu 14, which is the PID controller. And I just want to see when it's enabled. So I'll choose Menu 14, Parameter 8. That's a digital channel. And then to add it, I'll choose Select, like so. Now I'm going to map 3 analog channels for down here, so I'll uncheck digital. And what I want to look at is I want to look at, as I move down now, I want to look at the feedback, which is Menu 14, Parameter 21. So I'll choose Select. I want to look at the error, so I'll choose Select for that. Then I want to look at the parameter that the PID controller is adjusting, and that's Menu 1, Parameter 36. Analog reference 1, right there. So those are the 3 parameters, analog parameters I want to map here, and then one digital up here. So I'll click OK. And now here's my configuration. Down here, I'm looking at my analog channels, and if I want to look at my digital channel, I'll click here. So I'll do that first. And as you can see, it's PID1 enable, and I can change the trace color by clicking on it, but yellow works for me. So I'll just click OK. So that's my single digital channel that'll show up here. Now I'll go to analog channels. Channel 1 is my PID feedback. And I will choose a different color for that. My PID feedback, I'm going to choose bright green. So now I have my error, and yes, I will use red for error. And then analog reference 1. This I'm going to choose this cyan color here. I'll click OK. So there's my 3 analog channels and 1 digital channel. Now I'm going to come over here and I'm going to adjust the sweep. It doesn't need to be so responsive, so I'm going to change the scope sweep to 1 second per division. Now I'm going to test my communications. I'll click Start. And you can see there's a trace coming up here, but right now the PID controller is not enabled, so there's nothing showing down here. So I'm going to go ahead and get started now. I'm going to use my System On/Off button. There it is. And now I'm going to enable the PID controller. And you do right now. You see right now, the light blue here is my speed. The green is the feedback. And the red is error. So as the flow meter is increased now, you see my error being driven to 0. So it's working as it should. Now you'll also see my error is about 0 there. This is the output of the PID controller in terms of motor speed. So it's about 57 Hertz. Now one of the other nice features of this software is I can come up here to write parameters. And I can actually write 2 drive parameters right from within CT Scope. So the first parameter, first channel I'll enable is going to be, check my source again, I'm going to adjust my gain terms. So I'll open menu 14 and I'll choose menu 14 parameter 10, which is proportional gain. I'll enable that channel. Then I will choose menu 14 integral gain. I'll choose that and enable that channel. And I don't use derivative term. Derivative is not used very frequently. That the derivative term is the rate of change of error. And the update rate of the PID controller is 4 milliseconds. That's plenty fast for your average pump or fan. So let's just use those 2 channels. I'm going to check my communications here. That seems to be okay. Now, to make an adjustment. Right now my proportional gain is at 1 and my integral gain is at 0.5. So what I'm going to do is I want to keep my proportional gain at 1. And I'm going to change my integral gain to something less, 0.1. And then to write that to the controller, we'll go here. Now I'm going to induce some error. And as you can see, My system's pretty responsive, and I know that because the plot trace is pretty symmetrical here. This is the speed of my motor. This is the feedback from the flow meter. So as I'm inducing negative error, in other words, the flow rate is reduced, the speed of the pump increases. Basically, this is what I'm referring to when I'm saying trial and error. You need to go through this process to see what produces the best results for your particular machine. Thank you for watching this video. Be sure to look at the description for the video, as you'll find links to our technical support team, as well as a link to download the Connect project that I used for this demonstration. And as always, thank you for choosing Control Techniques.